Okay, quick little capture of me before I get. I wanted to go over those last few slides we missed in the displays and controls section, predominantly regarding controls. And this will be just for bonus questions that I'll put at the end of the exam on Monday. So take a look at these over the weekend, these slides, this presentation, this video, whatever you want to call it. And you'll be prepared to hear about the bonus questions. Then you don't bother watching this unless you're just interested in control design. Anyway, and it won't be very long. I just have somewhere in the neighborhood of 10 slides to cover. I'll try to do it in about. Now I'm going to switch over to the slideshow. Okay, so control labels. We were talking last time about some various characteristics of control design. We did talk a little bit about control response ratios, and I'll talk more about that in a few minutes. But labels such as the textual descriptors that go with control knobs, switches, buttons, etc., as well as perhaps symbols that label them, still are not the only method of distinguishing which control is which. You should have other techniques. Okay, the previous slide, I guess I can go backwards. You can see that even though this is really old and kind of awkward, even there the control themselves are shaped different. They probably have different texture slightly. The hand. So even with my eyes closed, I could tell maybe not which control is which, but I can certainly distinguish groups of controls. So that's one way of doing it. Labels are really important, and they should be considered at least the minimum, but that's not the only thing you should have. So especially if the speed of operating the controls is the only or is really important, you really shouldn't have labels only, because it takes a little while, especially if you have a lot of controls, to use the labels to identify the right control. And if getting a quicker reaction is important, then you need to have other means, such as the shape of them, their location, how they are activated, knobs, wheels, buttons, levers, etc., pedals. Another thing about labels is most of the time the label should be above the control, because you rarely reach down, which would be reaching over the top of the control to activate it. You almost always reach left, right, or even up to operate controls. Not always, but almost always. And so for that reason, locating a label above the control is rarely obstructed by the hand. So, if I'm reaching over the label to activate it, I may not realize which button I'm activating, which knob, or etc. Now, we did talk a little bit about control response ratios in class. I'll go over a little bit more just to make sure we're clear on that. The control response ratio is an actual ratio, but it's not really a ratio that we always actually calculate. We really just kind of want to know if it's small or big. So, for example, if I want to have a very sensitive control, that's on the next slide. For this slide, I guess I'll just say that the C part of the control response ratio is how much movement you need in the control. So, for example, if you're turning a knob, if you're moving a lever, turning a wheel, like the steering wheel of your car, etc., all of that is the control, the part that I'm able to move. And then the response, the R, is how much movement in the system you get. So, for example, that could be a lot of things. Movement in the system, right? It could be the actual dial itself that you're turning, like in your in the analog controlled stereos, right? For an FM dial, you turn the dial and you see how fast the needle moves. If it moves really fast or if it moves really slow, you can design it either way. It also would mean how much physical response you get, not just in in the needle or in the display, but actually in the system. So, if I hit the gas pedal, how far do I need to press to increase the speed by 10 miles an hour or whatever, to go from 30 to 50? How far do I depress the pedal? So, I could design a pedal that has to be depressed 20 feet to get that fast, which wouldn't be very effective. Or I could design a pedal that, if I depress it an extra millimeter, you're going to get 25 miles per hour of increased speed. That's probably not very effective either. So having a good balance there. So sensitivity and insensitivity. We'll make sure that you understand the difference between sensitivity and gain. Okay, there is no difference. High gain is high sensitivity. Now, let's make sure that you understand why, though, and how that relates to a low or high control response ratio. So expect there to be a question on those bonus questions at the end of the exam on this particular topic, maybe more than one. So a very sensitive control, that's one where I turn the knob a little and get a lot of movement in the system, okay? A lot of movement. So that's called a highly sensitive control. You would understand that, right? So if your mouse was very sensitive, right, you would slide the mouse just a little to the left or a little to the right, and you get this kind of movement back and forth with the cursor, right? That would be a very sensitive mouse. So let's think about how that relates to the control response ratio. If the control, the numerator, is very small, I move my my hand just a small amount, and I get lots of movement in the response. So low control movement, lots of response movement, that's a low control response ratio. The numerator is very small, low control, or a low movement of the control, gives you high movement, a lot of movement in the response. That's a low numerator and a high denominator. That gives me a low overall control response ratio. Would we agree? All right. The opposite is very insensitive control, or low sensitivity. That's when I move the control a lot, right? I'm moving it a ton right now, and all that's happening is the cursor's moving just a little. So if you've ever driven kind of large diesel engine type vehicles, large trucks, if you've ever driven a boat, like a sailboat especially, that has an old-fashioned wheel, then a lot of times, you can go around and around the wheel and only turn the rudder just a little each time you turn it, right? So you move a lot of control to only get a small response. So the numerator is very large, control movement is large, and the response movement is fairly small. So that means you have a high control response ratio, a bigger numerator than the denominator, high. We don't know what the number is. It doesn't really matter if what the ratio actually is, just to know that it's high. That's called an insensitive control, low sensitivity. Now gain, we generally say gain is the reciprocal of the control response ratio. Notice how a high CR ratio is low sensitivity and a low CR ratio is high sensitivity. Same thing with gain, right? A high gain, high sensitivity are the same thing. So a high CR ratio is a low gain. A low gain is a high CR ratio. They're reciprocal of one another. So gain is really just another term for sensitivity. Gain being kind of like a low CR ratio means I move the control just a little bit and I get a lot of movement in the system. I kind of get a gain, right? I kind of have a multiplying effect. Just a little movement gives me a lot in the system. That's kind of like, it's a gain. You're kind of increasing, maybe have an advantage, a mechanical advantage of some kind, etc. So that's what the word gain means. But what you really need to know is that gain is the same as sensitivity, and it's the reciprocal of control response. All right. Here's kind of a diagram that illustrates some of this. You can sort of see a lot of these are kind of older style controls. Low CR ratio is the same as high sensitivity and high gain. You can see that a small lever movement or a small rotating knob movement gives me a large movement in my little analog display up here. And then over here is the opposite, right? To get a large lever movement or a large rotation of the knob, it only gives me fairly small movement in the display. So this is an illustration of what we just said. Now, what do we like about that? Well, we like high sensitivity, therefore low CR ratio. We like that when we want quick and gross adjustments, when I need to make a big change, right? So I'm going to do a 180 in my car, right? I don't want to have to to do a 180 in my car, to turn around in the parking lot, I don't want to have to turn the steering wheel 14 times to make that turn, right? I want to be able to turn it just, 3/4 of a turn or whatever you need and make a really sharp turn, right? It's quick. It's a lot quicker to make that big turn, you know. However, for fine adjustments, I want to be precise, right? I want to go from 1.7 to 2.3. All right, I want to be accurate with that. That's kind of how it is on your digital FM dial, right? Where you want to go from 100.1 to 101.3, and you want to be able to get there without having to go back and forth a million times, right? So you have a fairly low gain, a low sensitivity in that control. I can turn it precisely a certain amount, and I know that I'm going to be able to move just a few little decimal places down the dial, right? That's when you need fine adjustment or precision. You want a high CR ratio. Therefore, there's some optimal value out there for any control design. Okay, so therefore you need to know the usage of your system. Who's going to use it? For what purposes will that system be used? What kind of adjustments need to be made with the controls, both the fine and the gross? The smallest and the kind of largest adjustments you can reasonably expect. What are the trade-offs of making one a little bit more difficult than the other, right? And then you balance that when you're designing your control response system. All right, so that's control response. Now let's talk about compatibility. This is kind of designing your control system to match up to what human expectations would have for it, right? And we talked about that with displays. We probably even talked about that 2 or 3 times with displays, and some maybe even with controls. Point being, it's really important. Okay, it's really important. You'll learn your system faster. In other words, a quicker learning curve. You'll have less reaction time because there'll be less information necessary to process applying the controls. So remember that when you're doing information processing and you need to make a decision, right, and you come to that, you're into the cognitive phase and you're moving on into the response phase, and you want to make decisions, it's a lot easier to decide on the events that you're going to react, I guess, to decide on what response you're going to have to your event, when the controls you need to operate are simple and they are compatible with how you expect them to be. So, for example, a steering wheel. I've learned to drive. I've been driving for a long time. I expect to turn the car with a steering wheel, and I expect to hit to increase the speed or decrease the speed using pedals. Right? What if I switch that? You could. I could steer with pedals. I could turn to the right to speed up or turn to the left to go down. How long do you think it would take me, no matter how much training I got, how long do you think it would take me before I was really going to operate that effectively every time? It would be a long time. Okay, that's a bad compatibility match, right? Even if you went through this entire explanation of how it was more effective because the design of the controls are really more optimal this way, whatever, it doesn't matter. It's incompatible with what I expect things to be like, and really probably incompatible with how my physical body operates. So I'd have lots of errors. I would be dissatisfied. I'd probably be slower reacting because I'd try to remember it. It would certainly take me a while to learn how to drive compared to a car that meets my expectations. So that's more about the cognitive expectations, my memory, my experience. But there are also compatibility issues with physical things. So just sometimes the controls could be designed in ways that I cannot perform them. What if I have to hold 2 buttons down that are 8 feet apart, right? That's just not feasible for me. Even if I stretched out completely on the floor, hands above my head, I'd barely make 8 feet. Maybe not. I'm not very tall. So it's really infeasible to have that. So, that's an extreme example, but there are lots of infeasibility designs that aren't as extreme that you maybe have to think about. So, typing the keyboard, right? Designing a keyboard that has certain systems. I have to press Control-Alt-Delete. All right. What if I just have one hand? So is Control-Alt-Delete a legitimate expectation on my current keyboard that I'm looking at right now if I only have access to one arm, right? One hand at a time. And why would that be? Well, maybe that would be because I only have one hand, but maybe that would be because the system I'm using, such as in a vehicle, right? I'm driving and I have to operate some system. Maybe having that 3 key pressing at the same time with only one hand is really difficult. So that would be a compatibility mismatch. So we want to look for all the compatibility mismatches, whether they're physical, what the physical capabilities are. Do I have to hit this, back and forth 17 straight times, left, right, left, right, left, right, left, right, and I have to do it within a quarter of a second, or it's going to time out, and I have to keep doing that for 30 seconds. I mean, is that a compatibility mismatch? Can we design a system that would work better than that? All right, let's see. Here's another example of some compatibility issues. So spatial compatibility. So this is a classic example. We've done some work in Ergo class with this in the spring semester sometimes. We even had a student project that looked at what student expectations are with this kind of layout. This is your stovetop, right? The burners on the top of your stove. They have lots of controls, right? Most of those controls are dial type controls, but you may have some button type controls, and you can control each one of the burners individually in pretty much every range I've ever seen. Okay, the problem is the controls are not. You typically don't put the control next to, like up here with the burner, right next to the burner, so that it's obvious that this goes with burner B or whatever, because it gets hot. You have things cooking. You don't put the controls probably on the surface, at least not right next to their burners, especially because you'll have to reach across one burner to find the control for the other one, and that could be really dangerous and be a hazard. So they're typically sometimes they're put on this front panel here. That's where mine are. In the old days, they would be on the back panel, which again, you have to reach across, but at least you can avoid a little bit of the burners by reaching high or reaching around or something like that. But because they're, well, look at the front, the first one here, A, B, D, C. Okay, does that make sense to you? A, B, D, C. Not just because it's A, B, D, C, but look at the orientation. A, B, C, D. So the ones in the back are on the outside, A and C. The ones in the front are on the inside. Does that make sense to you intuitively? Or does this more make sense to you intuitively? A, B, C, D. The ones in the back are on the top. The ones in the front are on the bottom. You don't see a lot of this design top and bottom. You usually see a left, right kind of design. Or would you want something else where the ones on it just goes kind of A is first, B is second, C is third here, and D is fourth. Is that intuitive? The problem is it's not a guarantee what's intuitive to you. Whoops. There's been a lot of issues with design. So are there ways that we can eliminate having to figure out, do I think that something in the back should be first or something in the back should be second? Okay, that's really the problem. And part of that problem is, well, really twofold. One is, this is in a different dimension. This is horizontal, this is vertical. And it's kind of a similar thing to when I say turn the wheel to the right. Well, there's no right or left on turning a wheel. You just have to decide, what do you think the right is clockwise. Most people think that. But it's not right because the bottom of the wheel is going left when the top is going right. Okay? There's no right or left, but we've sort of gotten used to, most of us, the idea that clockwise is right, turning to the right. Well, most of us may have gotten used to the fact that something that's higher is farther away in the back. Something that's lower is kind of closer to us, right? We've gotten used to that with road signs. The top part of the sign is farther away. It's kind of down the road, like if you look at the curve coming up or something like that. I don't know why we think that, but that's kind of high equals far, low equals near. But it's in a different dimension. And so you see that this little design here on the right, it's not vertical anymore. It's kind of angled, so it's kind of mimicking more of the horizontal control, right? So you can sort of see that A is in fact farther back because it's tilted a little bit. It's not just above it, it's actually kind of farther away. So kind of, whoops, going the wrong way there. Sorry. It's kind of better, but there may be even better designs, right? Where you kind of have some offsetting, or you even have, maybe you even have a label on both, so you can match them with the labels. The point is, this would be a problem if you got the wrong one active, right? If I think that burner B is going to be the one I turn on, or burner A, I should say, and I turn on burner B by mistake, I could burn myself. Certainly I won't cook my dinner the way I think. There could be some issues. What if I'm cooking two different things and one needs to be on simmer and one needs to be on high, and I get them wrong, right? So, that could be a lot of issues. So we definitely want to try to get this right. I wish I could say that all the new designs have it right, but I don't think they do. You should walk through like Sears or something the next time you're in the mall and look at all their displays of ranges and see what kind of differences you see. There's also movement compatibility. That's when when you see a display that's moving according to how you're matching up with the control. So, for example, if I turn the control to the right and it's a round dial, then the needle should move to the right, right? If I could, but unfortunately, there are other issues there, because a lot of times I've been turning a round control to move a display that's on a linear scale, right? That's kind of like your FM, your analog FM dial, right? So the old needle, you turn the dial to the right, and it would move the display to the right. But again, I say, what's turning to the right? It's not to the right, right? It's clockwise. So you turn it clockwise to move to the right. For most people, that's intuitive, but not always. So there are population stereotypes, as we've already said. People just expect things to be a certain way. Some of these are pretty strong expectations. Some of them, maybe it's the current trend, but the trend has changed over time, and it can change again. Some of them, though, are not going to change. We all drive cars. We learn to drive, so turning the steering wheel clockwise turns you to the right. So that's going to be a pretty strong expectation, that right movement of the system is achieved by turning a clockwise wheel or knob. That's just kind of how it goes. That doesn't mean that you're going to see that every single control is going to be designed that way. So let's talk about placement. So here's a knob, the blue thing. Here's a linear scale. Which way, not just which way do I turn the knob, but where do I put the knob? Do I put it here? So which way would I turn it to make it go up? Well, I'd probably turn it clockwise, right? Most people would turn it clockwise. And then you have the scale on this side, see the numbers, and then you have the needle on this side. Those are all things that you could do however you want. You can put the needle on the other side and the numbers on the other side. You can make this turn left instead of right, or see, there I go, clockwise or counterclockwise. You can make the needle go down when you turn it a different way, right? So a lot of things you can do. What about this one? Okay, which way should it turn if I want the needle to go up? Should it be clockwise or counterclockwise? Well, what about this way, right? Turns out that this one is the best design. So here's why. There are three principles, and you can expect a question on each of these three principles. Okay, I see that my slideshow is going a little bit longer than I said, but this is pretty much the end. So make sure that you learn each of these three principles. First is called Warwick's principle. It's also called rub theory. All right. All this means is the pointer moves on the same side as the control. Okay, so they kind of rub together. You see kind of how if you turn the knob this way and the pointer's over here, see how they're kind of, almost like they're rubbing together, right? There's just a narrow area in between here that's kind of moving, the actual direction of moving. You could almost imagine them kind of working like gears, right? They're kind of running together, right? That's Warwick's principle. Pointer is on the same side as the control. Got it? Okay. Scale side principle. This one's a little bit more difficult to understand. This is pointer will move in the same direction as the side of the knob that is on the same side as the scale markings. What that means is, first I look at the display. Which side of the display are the scale markings on? Well, they're on the left side. Agreed? Of course they are. They're on the left side right here. So then I look at the knob and I divide it into two parts, right? And I look at the left side of the knob. Left side where the scale markings are of the display makes me look at the left side of the knob. All right? Then I say, well, which way when I turn to the right, which way does the left side of the knob, the same side that the scale is on, which way did that move? Well, it moves up. So my needle should move up. That makes sense? When I turn it this way, clockwise, the left side of the knob moves up. And because my scale markings are on the left side of the display, my needle moves up when I turn clockwise. That makes sense? Think about it, rewind this, listen to it again. That's called the scale side principle. And that's really important. And the last one is clockwise for increase. We always have this idea, turning it clockwise, well, it makes the system go to the right or left. If I turn it counterclockwise to the left, clockwise to the right. But also, it's the same idea that turning it to the right makes it increase. All right, so I turn to the right, I'm getting a larger value. So that's clockwise for increase. All right, know these three principles. That lets you know where to put your control knob with regard to your display. And that finishes up. All right, so I went over about 10 minutes, well, 5 minutes. Okay, and you should be able to get some bonus points, up to 10 bonus points, if you can handle questions from this little presentation. Good luck.